Hi, welcome back. So we're in Chapter 6, Prediction by RCC, the outline prediction by classification to discuss the algorithm of decision tree. Well, basically the basic idea of decision tree, it says as follows. Maybe x6. X6, it corresponds to variable number 6, which is somewhere here. Let's say it's a continuous and I've been happen to ask is larger than or equal to a value. Let's say 91. Well, there are two possible answers, yes or no. Say, for example, no means I'm going to predict this as label 1. If it happens that is yes, I'm going to ask one more question. X2 feature larger than or equal to 65, no, make a classification to be -1. Otherwise, I'm going to ask one more question. X5 less than or equal to 1 whatsoever, no or yes. A classification may be -1 and 1. So reading this tree, regardless of the background of the person who is responsible to do final decision anyway, whether to consolidate any of these labels, as our guest says, it doesn't really require much of math background. That's one of the reasons I think it makes this decision tree quite a bit popular. So you could even construct decision tree for a regression problem. However, I would prefer classification problem when I have a discrete kind of output. But that doesn't mean that the other one is wrong as well. Okay, so let's see what are the steps actually we require to construct such a tree. We're talking about this splitting things. If I would have to draw this x1, x2, since here I have like x6, I involved x2 and I involved x1, I'm just like make some changes, like say for example x1 and x2. What does this value mean, 91? Means that variable x1, I am choosing a possible value here, 91, and then I am splitting that everything on this side of the line could be belong to one label and everything else belong to other label. But the actual fact here, we call this the node of the tree. And whatever comes here on both sides, it's called the leaves. The split, we have chosen x1. Next, we have chosen a particular value that x1 can take, that is a 91. So we have two important questions. Which variable we're going to start to create the node from? And the second question is, what is the value? And that's exactly actually what we are trying to do here. First of all, maybe we can create such thing called build a tree class. Taking a certain I, which is the training data, and say, for example, we're going to take a certain number of k. And k here will correspond to the number of possible children. In this case, like, for example, 2, since we are dealing with binary case, maybe it could be 3 or 4, whatever you like. This data set would be like x1, x2, and of course the label is in here. Let's make a condition. We want to ask a question just. How about if we take the absolute value of this I mean the total number here is the number of the I. So for example, I have 12 cases here. Is this number less than or equal to the k? If it is yes, let's set our label for the y hat into a some value. And of course, we're going to return that. But let's say else. Else means no. What I want to do, let's go for loop. And we say for each variable. As we said before, do not forget that we need to choose one variable to be the node. So basically here we say we're going to loop for each variable. And also the second point that we were talking about, the split value, let's call it the val s. Things to consider is to choose a certain split. And I'm going to show you in a while what is the best things you can do to actually choose a good split then. Say, for example, I started my loop with the first x1 and I have picked up a certain split. Somehow I started to slice my space. Then we will have two different regions on the right hand side or left hand side. It's like, say for example, I positive, another one, let's call it I negative. Where the I positive is belong to one class, every data point I have here, ith data point, will be actually member of this I given data point of that x of I to be larger than or equal to this particular value. Something like this. I mean, I'm just showing you the Sudoku code. Same thing you can do for the next one. The I minus is going to be less than the S. But once we do that, we're going to make our guess. Now, what I'm saying here, let's look at this and take the average of all the labels here. So it's most likely at this region, I guess my y hat is going to be minus, for example. In this region, I guess my y hat is going to be positive. Okay, now this is actually my sort of f of x that we were talking about, the first step of our framework. So in the next step, what we have to do now is to calculate the error, which is called the loss function. There are many of them. Let's choose one we all know and love called the least square. So after this loop over all the x's, I will return the minimum, the best choice of variable and s. And based on that, this is going to be my node. Here's an example. We have selected this x1. How? Actually, we have tried x1 and x2, and we found out that x1 with this split value happens to be with less value of error. Now, the first node has been established with the both split. So what I'm going to do, I will say return, but this time I want you to return a node whereby it has the following element. First, it have the var and the s, the right hand side and the left hand side. And here is the point. What we're going to do with these right hand side and left hand side, all these points in here, we're going to now put these and pass them again to the exact same class. We call it building tree. These are the actual procedures we do in order to construct the decision tree. Let's actually try to construct decision tree. Let us assume after I did this first loop, I found out that x2 with the split value larger than or equal, say, to 0.28 is the best split. Okay, it's my first node. I am splitting my data, looks like this. I have two sides, the I minus, as we said, the I positive. Now I am taking everything here and I'm putting back again for that same loop. Say the left hand side have chosen x1, for example, larger than or equal 7.2. I'm gonna make a split here. Once again, we would have like a right hand side and the left hand side. Do not forget, when we started very much in the beginning, I told you there's the if condition and the else condition. And I told you back then, we're going to get back to this again. And now I'm getting back. Now, the actual question I'm asking, how many data points are there in this region? There are 2. So I'm asking, is 2 less than or equal to 2? That's yes. It means I'm not going to this else. Here I'm going to terminate and I'm going to do something. We'll say we would take again the average over all the point that I have. Now on the left hand side, how many points I do have? I have like 7 of them. So this condition is not working. Again, I'm going inside here, looping, splitting down maybe a new line here. One thing I wanted to show you, if you reach out to this side here, you'll figure out that actually you're going to split one more time here until this condition becomes true, and then you stop. But basically, it's not going to make much of a sense when you look. Both sides are actually 1 and 1 in both sides of the leaf. We don't even need this split. I mean, we should have stopped. And here, even the error was almost close to 0. So what we could do can actually save a lot of time and effort, and efficiency become better by actually regularizing this term error. Something similar, so we can add lambda. We used to multiply that by the length of the alpha. But here we're going to multiply by actually the number of the data. In this case, like let's say here, the number of I. And this regularizer will make a difference when we reach out to this particular point. You will see that we're going to stop. So if you go over this algorithm, try by yourself on your own, and you will figure out that it makes a huge sense by then. There are many different other material I've seen myself talking about the use of the entropy, then the gain information, and etc. You might also want to check that on your own, but I personally found practical way of looking at this algorithm. I would have rather explain what I have just done here. So next, actually, we'll be looking at new kind of algorithm called the support vector machine, or the SVM. That's exactly what I'm going to do next. I will see you then.